4 or 5 Exponential Growth and Decay Modeling Data, Day 1. Your learning goal is that you'll be able to model exponential growth and decay and use logistic models. So for these models, let's start with the growth and decay. This is how the model looks. A model is just like an equation. And it can say f of t, or you can see it as just a. And I'll explain what everything means. So a of 0 is your original amount. And what you're doing is you're trying to look at how something grows or decays at a certain rate over time. So k would be the rate of how something is growing or decaying. So if k is larger than 0, it's growth. And of course, if k is smaller than 0, then it's decaying. And then t is your time, and they'll tell you if it's in years or days, or they'll give you that actual unit. And of course, E is the key on your calculator. So looking at example 1, we're looking at the growth model for the U.S. population, and we're looking at, if you look at the table, they're showing from 1970 through 2007. So we're looking at the population. And it says in 1970 it was 203.3 million, and by 2007 it had grown to 300.9 million. So A, find an exponential growth function that models the data for 1970 through 2007. So I'm going to write our model. Remember, it's the same for growth and decay. And we have the original amount, because that was in 1970. It was 203.3 million. And then we have what it grew to, which was 300.9 million. And E, remember, is the key on your calculator. We don't have the growth rate, which is what we're going to find. And then T, that's the number of years. So if you look at from 1970 to 2007, how many years is that? So that would be 37 years. So first, to have a growth model, you have to have your original amount and your rate. That's all you really need. Everything else helps you to solve the problem. So we need to find K. So the first thing we would do is divide both sides by 203.3. And you can leave it as a, I don't know why I crossed that out. I'm sorry. I didn't mean to cross that out. You can leave it as a decimal, or you can leave it as a fraction. And from here, this is our exponential equation. So I'm going to go to our log form. So ln, our base is E, of the number is equal to your exponent. So that's your base, exponent, and that's the number. And then whatever you get, you're going to divide by 37. So I'll quickly divide that. So we will get, or you should get, 0.010. I'm just going to go to 4 decimal 6. So when you write the model, it's going to be A equals my original amount, which was 203.3, E to the 0.0106 t. So this is your model. Then the second question, which was letter B, says, by which year will the U.S. population reach 315 million? So now we have to solve for T. So I'm just going to plug in 315 because that's what we want it to grow to. And you basically do the same thing. You divide. Oh, you don't divide that though. Now, and then you're going to write it in log form. ln base E of your number is equal to 0.0106t. And once you put that in your calculator, you're going to divide. And let's see what we get. So it's going to take about 41 years for it to grow to that amount. And since they want what year will it be, you would take the 1970, because that's what we started with, and add 41. So that would give us approximately the year 2011. In example 2, we're going to talk about half-life. And that just means that if you remember in your exponential growth equation or decay, your final amount is half of the original. So this is how it would look. So it says, carbon-14 dating, the Dead Sea Scrolls. Use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. Anytime they ask us to find the model, they're asking us to write the equation. So we're going to use our half formula. And it says that this was after 5,715 years, so that is T. So now I'm going to solve for my decay rate. So I'm going to divide by 2. And now I'm going to write it in log form. So it's ln base E of 1/2 is equal to 5,715K. So then I divide. And what's going to happen is this number is very small. So it's probably going to be written in scientific notation. So it's going to look like 1.21, and then you'll probably see an E to the -4. So that just means you're going to move the decimal place over 4 places. And it's negative. So when you write your model, because they didn't give us an original amount, it'll be negative 0.000121T. Example 3 is an example of a logistic model, which is modeling the spread of the flu. And basically what that means is this model shows that over time, growth is always limited. So there is a limited amount that something on Earth can grow. And so this model describes a number of people, F of T, who have become ill with influenza T weeks after its initial outbreak in a town with 30,000 inhabitants. And so because there are only 30,000 inhabitants, this number is our limited size. And for part A, they want to know how many people became ill with the flu when the epidemic began. So when it began, our t-value is 0. So you're going to actually plug in 0 for t. And you're going to plug this in your calculator. And if you do that, make sure the numerator has parentheses and the denominator. And you should get approximately 1,429 people. Okay. B, how many people were ill by the end of the 4th week? So now you're going to plug in 4 for t. And you're going to do the same thing. But make sure there are parentheses around the numerator and around the denominator. And you should get about 28,583 people. And then C, what is the limiting size of f of t, the population that becomes ill? So according to this model, remember the constant number which is on top represents that limited size. Because there are only 30,000 people in this town, that is the limited number of people that can become ill.